All right, can you all hear me?
Yeah.
Okay, good. I hope the exam was okay. What I want to do in this remaining hour, maybe 55 minutes or so, I want to start talking about chapter 33. Okay, just some reminders. Your motor lab is due on the 25th. The scope video is due tomorrow. That shouldn't take very long, I hope. Because all you got to do is just show me that you know how to measure a signal on the scope. Okay. And then I want the transient circuits is due on December 1st. All right, so today I want to talk about AC current and RL and RC circuits. And then next week I'll do the main one, which is the RLC AC circuit. And there's going to be a lab associated with it. Okay.
Professor?
Yes.
So on the scope video, you just want it hooked up straight to the signal generator and then show that we can take measurements off of that?
Yeah, that's it. Basically, all you got to show is that you can measure voltage and frequency.
Okay, got it.
Yeah. Yeah, that's it. And that way, the last two labs we do, you're going to be able to do the measurements. I just want to make sure that you can do the measurements before you actually do them in the subsequent labs. Unfortunately for us, we only have, that scope only has one input. Ideally, it would be nice to have one with two inputs, especially for the last lab. So if I get to the demo today, and I'll figure out a way to get to the demo today, I'm using a two input scope so that you can actually watch the voltage from the power supply and the voltage across the resistor. And so you can do comparisons. Okay, that's the big advantage of having the two input ones. So, but anyway, you guys are stuck with the one input one, so we can't really do comparisons. And you'll see what I mean when I show you the demo. Okay, questions before I get started?
Professor?
Yes.
For the scope video on Canvas says it's due tonight, the 13th.
I'll change it. Sorry.
Okay.
Thank you. Thanks for pointing that out. Okay. Any other questions? All right. So, oops. Make sure I didn't mess things up here. So we want to talk about AC current. So what that means is we want to take a circuit and we want to drive it, not with a battery, but with a voltage that's time dependent. And I want to talk about what AC current is and compare it to DC current. DC current means that the current is in one direction. So if you plotted voltage as a function of time, something that's DC obviously would be this, like a battery. It can also be something like this that doesn't change direction. I mean, when I showed you an example of the generator, that generator, the way I had it set up, would actually produce DC voltage. And so the voltage it would produce would look like this. It always was in the same direction. But because I had the split ring, when the coil flipped by 180 degrees, what you would get is you would never get the voltage to go negative. And so basically you would have a voltage, an induced voltage that was always positive. So even if it varies, as long as it goes in the same direction, we will consider that DC current. In the case of AC current, the current changes directions. So that's the difference between the two, alternating current, direct current. Okay, alternating current, you'll have the current doing this, and also the voltage. That's one example. Another example would be the square pulse. And they're periodic. Generally, the waveform that we use for AC is periodic. I mean, you can create those that are not periodic, but they're periodic. And the sine wave is easy to produce because all you got to do is rotate a coil in the magnetic field. The square wave is much more difficult to produce. The triangle wave is also difficult to produce. Okay. But it can be done. I mean, a square pulse is not perfectly square, but it's approximately square. So the primary problem in this chapter is given an AC voltage, we're going to drive our circuit with an AC voltage. Okay. Find the current in the circuit. Whether the circuit has a resistor, an inductor, a capacitor, or any combination of them. And we're going to really focus on fairly basic circuits. We're not going to do problems involving Kirchhoff's laws with AC circuits. Okay. They tend to be a little bit more difficult. I mean, they tend to be a little more difficult, but you guys have the background to be able to do them. We just don't have time. So those of you folks who take Engineering 17, you'll cover those kind of circuits. So I need to introduce to you some standard notation that we will be using when we cover AC circuits. So we're going to use small letters to represent an instantaneous value. Because voltage and current will depend on time, and we need to differentiate between amplitudes and instantaneous values. So anytime I write V, a small v here, it's not going to represent velocity. We're not going to be talking about velocities of particles in this chapter. So a small v means instantaneous voltage, and a small I means instantaneous current. Capital V's and capital I's represent peak values, or what I mean is this value in the graph, also known as the amplitude. And then we're also going to talk about the RMS value, which is related to the peak value. Your multimeters measure RMS values. So let me go back. I will write RMS as a subscript when we're talking about RMS values. So first question is, if I use an AC power supply in a circuit with a resistor, does Ohm's law still apply? And the answer is yes. Now I got to be specific. I want to talk about specifically what kind of AC power I'm talking about, what kind of alternating current. We're going to focus on the circuit where the power supply voltage varies sinusoidally with time. Okay? So all our power supplies, delta V of the supply, will be written as V max cosine omega t. Why did I choose cosine as opposed to sine? I can use sine or cosine. They just differ by a phase factor. So the convention is to use cosine, except your textbook uses sine. Okay? Your textbook is, I think, the only textbook that uses the convention sine, which is kind of unusual. Okay? The engineering books will use cosine. So we want to take a look at how this applies. So we have a power supply. And this will be our symbol for the alternating current power supply where it alternates sinusoidally. So we're driving with a sinusoidal signal. There's our resistor. And we know that the voltage is I times R. So I don't know if you noticed, but now that we're in chapter 33, and the books will probably do that too, they will always drop the delta symbol. Okay, so I'm going to try to keep writing it on the board. Okay. So the question is this still valid? It turns out it is. V and I will change with time. Okay. But their instantaneous values follow Ohm's law. So basically, if delta V is V sub m cosine omega t, then I is V sub m cosine omega t over R, sorry. And then we can define V sub m over R as I max. And so now we have the expression for the current in our circuit. If you were to plot a graph of voltage as a function of time and current as a function of time, since these two basically differ by a factor of R, they're going to be in phase. Now, what does that mean in phase? Anybody can tell me what does that mean? Because sometimes people have a hard time with the terminology. What does in phase mean?
It's the same period, right?
There's the same what? I'm sorry. It means the peaks come at the same point. The zeros come at the same point in time. And the troughs come at the same point in time. That's what it means.
So they cross the axis at the same point? Is that the...
Yeah, they cross the axis at the same point, and
Okay.
they peak at the same point, and their minimum at the same point. There's no phase difference. When you talk about something sinusoidal, the point, this x-coordinate on the graph, or this point on the graph, the x-coordinate represents the phase, what part of the trigonometric function you're at. Okay, I'm saying it very in an informal way. Okay, so the phase is basically where this point is at, what part of the cycle you're at. Okay, and so if you have two functions who get the same value at different points of the cycle, then you say that they're out of phase. So oops, that's not correct. See, the value at the same height comes at different values of time. And so then you say that the two functions are out of phase. And the phase difference is the difference in time. Well, it's related to the difference in time between those. You got to convert that to an angle. Does that make sense? So if they're a quarter period off from each other, they're going to be pi over 2 out of phase. Does that make sense? I just want to make sure the terminology is understood, because when you folks take 215, you're going to hear that term a lot. You're going to be a large portion of 215. You focus on something called interference, and whether your ability to identify whether you get constructive or destructive interference will depend upon you understanding what phase difference means. So here's our expression for the current. Pretty straightforward, okay? Pretty straightforward for Ohm's law. Now, question is, when you measure voltage with a multimeter or current with the multimeter, does the voltage that you see on the multimeter change with time? You actually don't see the voltage change with time. You don't see it change periodically. And one of the problems is if it was able to do that, you wouldn't be able to notice it anyway, because the frequency for a typical signal that comes out of your outlet, the frequency is 60 hertz, and omega is 2 pi times 60 hertz. Remember, omega is just an angular frequency. This means that the value on the multimeter would change 160 times a second. Your eyes can't pick that up, okay? And so the multimeter measures some sort of average, but it doesn't measure the average voltage, because what is the average of a sine function or a cosine function in one cycle?
Wait, 0, right?
It's 0, so it would always read 0. Okay, so we use another way to measure to display the voltage or the current. And it's related to the power. Now the power is I squared R. Okay, so the power is I squared R. So what would be I effective over a cycle? What would be the effective current over a cycle? Well, you'd have to figure out the average of the power, which means that you have to figure out what the average of I squared is. And that's not 0, because I squared is always positive. And so what we do is we look at the average power in a cycle. Okay, so the average power is going to be I max cosine omega t squared times R. And all we got to do is figure out the average of this function. We got to average power over one cycle. So how do you find the average of a function like this? From calculus, how do you find the average of a function? Well, you got to take the integral of the function from basically omega t equals 0 to 2 pi. So from omega to, from t equals 0, t equals 2 pi over omega. And then you got to divide by 1 over 2 pi over omega. That's how you find the average of a function. I think you learned that in Calc 1 or 2. And so you'd have to integrate this and get the value. So there's also an intuitive way to do it. Okay, there's also an intuitive way to do it. And so what we're going to be able to get out of this is, what is the effective current? Because what I want to do with this, I want to say I squared effective times R, okay, is going to be equal to I max squared R times the average of cosine squared omega t. So I effective, hopefully I'm not too far down, squared is equal to I sub m squared cosine squared omega t average. Okay? So all I got to do is figure out the average of this function. So we know that the average of cosine is 0. And we know that the average of cosine squared is not 0 because that function is always positive. How about if I rewrite cosine squared and then take the average? Using a trig identity, let me make this bigger. Using a trig identity, I can write cosine squared as 1/2 times 1 plus 2 cosine of theta. Now, what if I take the average of that? What am I going to get? What's the average of a half over a cycle?
Just a half, right?
Okay, it's a half. I know it's a weird question. What's the average of cosine of 2 theta over one cycle?
It's 0.
It's 0. So basically the average is a half. So the cosine squared, the average of cosine squared omega t, the average of this is just a half. And if you want to prove it, then evaluate the integral and go through the process. I'll let you do that. Okay. So we get I squared effective is equal to 1/2 I squared max. So then I effective is equal to 1 over the square root of 2 I max. And we're going to call this the RMS current. And so this is the root mean square current. And so this is what your multimeter measures. Okay, your multimeter measures that value. So if you actually took your multimeter, and it does the same thing with the current, with the voltage, took the multimeter and just shoved the leads into the light socket, or and not the light socket, but the plug, it would say 120. That 120 is the RMS. And I sub m then, or V sub m then would be the square root of 2 times 120 volts, which comes out to around 170 volts. So are we okay with that? So when you're doing, when you're measuring AC current, AC voltage, you have to remember you're actually measuring an RMS value. Now on these multimeters that we use, this one actually has a setting for AC current and voltage and the setting for DC. On some of them, like the ones we have in class, you have to press a button to go from DC to AC, which everybody, when they do their experiments, they forget to do that. Okay. So again, VRMS is just 0.707 Vmax. And so like I said, what's coming out of your outlet, your regular outlet, is 120 volts. That's an RMS voltage. The actual Vmax is about 170. It's going to be 120 times the square root of 2. So, just so we understand this, suppose we have a triangle signal. can we figure out the RMS? Let me expand that, that's too small. Can we figure out the RMS voltage for that kind of signal? The same process, we got to take the average of that function squared over a cycle. And then we get the RMS voltage. Before I answer this question, do you know why we use AC current in the home as opposed to DC current? Anybody want to venture to guess why we use AC?
Is it because it's safer?
Well, I don't know if I actually would argue against that because AC oscillates at 60 hertz, which is about almost the rate at which your heart beats. So it's actually, to me, not as safe because that's going to really mess up your heartbeat if you get electrocuted. But it's really based on this. For a DC, if you average both over one cycle, you average the power loss of the energy that's delivered to your home in one cycle. P is going to be I squared R. It's always going to be that for DC. But for AC, because the average of this is 1/2, for AC, you always lose a half. And this is independent of whatever frequency you're using. So in Europe, they use 50 hertz, for example. It doesn't matter. You lose half the energy. So it's a little bit more energy efficient. So let's try to do this one with a triangle function. And I want to see if you guys think of well, let's see what the results we get for this one and compare it to AC. So here we lose half the energy. As compared to DC, I should say. So let me draw my signal. It's a triangle. It's a repetitive triangle function. So this is 0, this is the period t, and this is Vm. And so I want to find Vrms for this particular type of signal. So I need to figure out what V is. How do I write V? Do you all agree with me that I can write V in the following way? Are you guys okay with this, the slope times time? Any objections or questions? Okay, I'll move on. Then V squared is V sub m over the period squared times t squared. And so I want to find the average of this. I guess I don't need this subscript, but... And to do this, I got to take 1 over the period times the integral of 0 to t of this function. And this one's not hard to do, right? I mean, the integral of t squared is what? What's the integral of t squared? Anybody?
T cubed over 3.
T cubed over 3. So this is going to give me 1 over t times v sub m over t squared times t cubed over 3. So this will end up giving us v sub m squared over 3. I want to take the square root. I want the RMS value, so I got to take the square root of the average of this function. So VRMS is the square root, the same thing with IRMS, is the square root of the average which is V sub m over the square root of 3. So notice that if I use V squared over R, this actually would, if I used this signal to deliver energy to your home, I would actually lose even less energy. Why don't I use this? Why don't I use the triangle function?
So it's harder to produce?
It's harder, you're right, it's harder to produce. Okay, so to produce this, you actually need a linear combination of sines and cosines. And you will, those of you who are engineering and maybe some computer science majors, you will actually learn how to write this as a series of sines and cosines at some point. Okay? All right, so we'll continue. So we do tend to talk about things in terms of RMS voltages and RMS currents. And like I said before, the standard AC room model is 120 volts RMS, so the V max is about 170. You take 120 and multiply by the square root of 2. So, in doing problems involving AC circuits, you generally have to apply Kirchhoff's loop rule or Kirchhoff's current rules and solve the problem. So you got to solve a differential equation, which is beyond the scope of this class, especially for some of the circuits we do here. But fortunately, because of the fact that we're going to be using a sinusoidally varying function, there's a nice technique that allows us to analyze AC circuits. And they're called phasor diagrams. And phasor diagrams will also be used in Physics 215. So I'm going to introduce to you this mathematical topic that's only used in physics and engineering courses for analyzing circuits and maybe talking about some phenomenon in Physics 215, where the main function you're dealing with, the driving force, is something that varies sinusoidally. So I need to introduce to you something called a phasor. Okay, this is not a weapon that not like the weapon you hear in Star Trek. Okay, so this is a phasor. It's a mathematical construction that's going to allow us to understand what's happening in a circuit with an AC power supply, a sinusoidally varying AC power supply. So phasor is basically a vector that's placed in a standard XY coordinate system. And is used to represent a physical property that changes periodically and sinusoidally. The length of this vector represents the maximum value of the property. This vector rotates counterclockwise at the same frequency as the property it represents. But we're only going to look at it at an instant in time. So, so this thing for AC circuits, and this is rotating 60 times a second. Okay, so it's basically this vector, you can imagine this vector that rotates 60 times a second, and we're only looking at it at one instant in time. Okay, so the length of this vector, for example, would represent V max. the projection of this vector onto the x-axis represents the instantaneous value. In other words, the dot product of that function, of this vector with respect to the x-axis, gives you the instantaneous value of that property. And you can always display more than one phasor in the same coordinate system. And so the result is a phasor diagram. And you can add phasors. And you add them just like you would add vectors. Generally, when we're analyzing an AC circuit, we're more interested in these quantities, the maximum value, as opposed to actually the instantaneous value. They help us to visualize what is happening in an AC circuit. They're not real physical quantities. They're a mathematical construction. Okay. When you do interference in 215, you can use this idea also. And this comes from the fact that we can write the power supply voltage not as a sine or cosine, but we can write it as a complex exponential using the Euler equation. And if you imagine plotting the x-axis as the real part and the y-axis as the imaginary part, if you've done some of this in your calculus courses, it's really related to that. So let me give an example with AC and resistors. So the graph I show you here, let me blow this graph up. The graph I show you here shows you the plot of the voltage as a function of time. And it shows you a plot of the current as a function of time. The blue is the voltage, the green is the current. Now the graph on the right, the phasor diagram on the right represents the maximum voltage and the maximum current. They're at the angle omega t. It also shows you the projections of V and T onto the x-axis. Those projections, those vectors you see along the x-axis represent the actual value of the voltage or current at that particular time. Are we clear on that? And since both V and I are in phase, you'll see that the arrows that represent V and I are overlaid on top of each other. And in fact, for any resistor, the voltage and the current are always in phase. The voltage across the resistor is always in phase with the current through the resistor. That's always the case. So I had a faculty member created this little thing in PowerPoint to show you what happens in one cycle in a phasor. So these things rotate counterclockwise. Now, when the person generated this, he was using the convention of the textbook. These should really start on the horizontal axis, but this one did not. So these rotate counterclockwise, but they should have started on the horizontal axis. But he used the convention in the textbook. And they're just showing you once what happens over a cycle. Actually, I'm doing 2 cycles. So that's what phasors do, okay? The reason why I introduced this is because in order to look at circuits that have inductors and capacitors, we have to draw the phasors. It's actually a little bit, we can actually get the information from the circuit a little bit easier. As opposed to solving equations. Although this circuit that I'm showing you right now is a fairly straightforward circuit. It's a circuit with an inductor and a power supply. Let me change views here. So let's say we have a circuit with an inductor. So one caveat here. I'm going to assume that inductor is ideal. What do I mean by that? What do you think I mean about that? I'm assuming.
You mean that has?
Say that again.
It has no resistance?
Yeah, it has no resistance. Of course, all real inductors have resistance, so we're going to assume R is 0. Okay, or if there was a resistor in the circuit, then we would assume its resistance is small compared to the resistance in the circuit. And so we want to look at the voltage and the current in this circuit. Of course, we know that the voltage across the inductor has to be equal to the power supply voltage. Or you only have two elements. So we have so what we want to do is look at the current in the circuit. We know the power supply voltage is going to look like this. And let's see, I can divide both sides by L. And then multiply both sides by T. So I can actually figure out the current. All I got to do is what? I have to integrate. Okay, and I'm going to integrate I will integrate this from 0 to whatever I is. And I'm going to integrate this from 0 to whatever t is. So maybe I should make these a prime. And so when I perform the integration, then I'm going to get, what's the integral of cosine? It's sine, and I get a 1 over omega. And of course, sine is cosine omega t minus pi over 2. So let me write it this way too. And then this is the angle measured with respect to the power supply voltage. Okay. So this is the angle measured. So we could compare this, the phase of this, to the phase of our power supply voltage. Okay? Now, I want to, before I talk a little bit more about the phase, I can write this current expression like this. I max sine omega t where I max is the power supply voltage divided by omega L. And we give omega L a special name. We call it X sub L. And we say X sub L is called the inductive reactance. Okay, so omega times L, we denote it as X sub L, and we call it the inductance reactance. Now let's take a look at the graph. Let's take a look at the voltage and the current. Okay, so if we take a look at the voltage and the current, you see that the voltage is ahead of the current by 90 degrees. The voltage leads the current by 90 degrees. Do you guys see that? There's a 90-degree phase shift. And so we say that the voltage leads the current in an inductor. Okay? So for an inductor, the voltage leads the current. You can either remember it as the voltage leads the current or the current lags the voltage.
Why does this happen?
Well, because of the fact that delta V is L di dt. The voltage across the inductor depends on the derivative. It depends on the derivative of the current. Does that make sense? From Faraday's law. Right? From Faraday's law.
Yeah.
Because what's the derivative of a cosine? You get a sine, right? So it's because of Faraday's law that there's a 90-degree phase shift between the two. Remember, what I've said, though, is that this has no resistance, and I don't have any resistance in my circuit yet. Okay, I don't have any resistance in my circuit. Questions? Guess what's going to happen when I do a capacitor? So we'll see what a capacitor does. So V sub L then is the voltage across the inductor. Instead of writing it as L di dt, you can just write it as I times omega L. So we're trying to make it look like Ohm's law. I've written it so it looks like Ohm's law here. Okay? So omega times L we call a reactance, the inductive reactance. And so the voltage across the inductor then, the maximum voltage across the inductor is just I max times X sub L. Okay? So we can in general say of course, this is going to be obvious for the case when you have just the inductor in the circuit, but this is true when you have an inductor and a resistor. Let's say if I put a resistor here, this is still going to be I max times X sub L. Of course, in this particular case, V sub L equals V sub M. Remember, this represents the maximum value. I'm not writing it as a function of time. It's written as a function of time here, and the current's written as a function of time here. But I'm really going to be focusing on the maximum value. And if I want the RMS value, I take those maximum value and divide by the square root of 2 to get RMS values. Okay. And so this inductive reactance is a measure of the opposition to a changing current. We talked about this, that inductors oppose changes in currents. So this inductive reactance really is a measure of the opposition to a changing current. And notice that X sub L increases with increasing omega. So the frequency increases as the sine function varies more and more, di dt is going to be higher. So we are X sub L. Remember what Faraday's law says, right? If you have a big change in flux, then you're going to have a bigger induced EMF. Okay, so in the interest of time, I want to do the capacitor. So I'm going to do let me do the capacitor first. And then I'll come back and do the ones with the inductor. I'll come back to it. So let me do the capacitor in the interest of time. And then, so I'm just going to I'll do the RL and we'll talk about RC next week. Or I might mention the RL one in lab next week. Okay, I'll think about it. So let's say we have a capacitor. So let's replace this with a capacitor. All right. Now what? Now what's delta V equal to? Well, it's Q over C, right? So is I going to be equal to? And so this is going to be V max cosine omega t. Now, Q is going to be C times V max cosine omega t. I should make a small q. Then I is dq over dt, which is going to give me what? C V sub m omega sine omega t. Oh, there's a minus sign. And so this is the same as writing that. Remember, this is Q max times omega. I want to write this so it looks like Ohm's law. So I got to write it like this. Or I can write it with the sine function. And so that means I'm going to define x sub c equals to 1 over omega c. And I'm going to call this the capacitive reactance. And I'm defining this just so it looks like Ohm's law. So I can say V is I times, the voltage across the capacitor is I times X. So now the phase shift is negative because we're measuring, again, measuring relative to the power supply voltage. So I know you see a positive there, but this is a negative phase shift. And so if you plot voltage and current as a function of time, you will see that the current is actually ahead of the voltage by 90 degrees. The current leads the voltage. So you can say the current leads the voltage by 90, or you can say the voltage lags the current by 90. Does that make sense? So there's your phasor. You have to know how to draw the phasors, okay? You guys have to learn how to draw, because I'm on the test, I'm going to make you draw phasors. So make sure you understand how to draw them. Okay. And this one's pretty straightforward. So I've drawn the voltage across the capacitor, the current. My labeling is bad. That labeling, the I sub C and the V sub C, the I and the V should be capitalized. I think I think the reason why I put those there is because it's too hard to write them next to the omega t plus pi over 2. So the voltage lags the current in this particular case. And so the question is, can you draw a circuit for the RC, a phasor for RC circuit? And I think you'll be able to draw it once I do the RL circuit, which I'll do on Monday. Okay. So let me show you an example of an RC circuit. This is not truly an RC circuit because I actually have a resistor in my circuit, but I'm cheating. But if I set this frequency correctly, you'll notice the 90-degree phase shift. Just give me a second here. Okay, so I'm going to switch to my camera. So I have, it's not a truly, I have a resistor in the circuit, I'm cheating. Let me change. So the yellow signal is the power supply voltage. You all see that? I could bring this closer. And the orange signal is the voltage across the capacitor. Do you see they're 90 degrees out of phase?
Yeah.
Okay. And really, I'm kind of lying to you. I set it to the right frequency. I actually have a resistor in series because I'm going to use this circuit next week in lecture. But I set it to the right frequency so that the phase shift is about 90 degrees. Okay. But this acts just like a circuit where there's just a capacitor in the circuit, and that's it. And we'll talk about what the effect of the resistor is. I think I'll do it on Monday. Okay. Any questions? Okay. So I'm going to stop here because I actually have to run to a meeting, which was supposed to have started at 2. All right, so you folks have a good weekend. I hope the exam went okay for you guys. I will talk to you later.